the honor to introduce our lecture today, the Sari of the Hebrew University of Jerusalem. As you might have guessed, Professor Sari is an astrophysicist. He received his PhD from the Hebrew University, summa cum laude, with a thesis on gamma ray bursts. He then spent 10 years at Caltech, first as a postdoctoral fellow and later on as an associate professor for astrophysics and planetary science. And in 2007, he joined the Hebrew University as a full professor of astrophysics. Professor Sari has published over 100 articles in professional journals on subjects like the physics of planetary systems, gamma ray bursts and their afterglow, and dynamical processes in galaxies. And for his outstanding research, he has received an impressive list of awards. I cite as an example one of them, the Warner Prize of the American Astronomical Society, which he received in 2006 for, I quote, his diverse contributions to the theoretical understanding of relativistic explosions, gamma ray bursts, and the dynamics of solar system bodies. Since 2008, he is also head of the Teva Amirim program, which is an honors program for undergraduate students here in Israel. And since 2010, he also serves as chair of the Bloomfield Science Museum here in Jerusalem. And in today's lecture, he's going to tell us something about the formation and evolution of planetary systems.
My talk will be about formation and evolution of planetary systems, but maybe I'll start with a broader view of astrophysics. I'm a theoretical astrophysics. It means I'm not doing the actual observations, but I'm trying to understand how the systems that people observe in space work. And as such, I have the luxury on working on a large variety of objects, from the formation of galaxies, asteroids and their formation or their impact on planets, dynamics of galaxies and stellar ejection from galaxies, as you see there on the top left, explosions of massive stars known as supernovae and gamma ray bursts, Kuiper belt objects, which I will talk about, and so on. So there will be another discussion talk later, and if you want to ask about any of these subjects, you're welcome. נפעיל את המיקרופון. So let me start this talk by making sure that we're all on the same page and we all know what a planet is and what a star is and what the difference between them. So if you go outside to the night sky and you look in the sky, see all these dots. What are these dots? Most of them are stars. Most of them, not all of them, but most of them are stars. Just a few of them are planets in our own solar system. If you have really good visions, you can see a galaxy. Maybe you can see Andromeda. It's somewhat difficult, especially in today's environment where we have light pollution all over the place. Okay, so stars are very abundant. These are all the dots we see on the sky. And they're basically similar objects in nature to our sun. They're made out of the most abundant material in the universe, which is hydrogen and helium. 3/4 hydrogen, 1/4 helium in mass. They have different masses. Some are bigger than our sun, some are smaller than our sun. So it turns out our sun is an average star. Not too big, not too small, not too bright, not too dim. In order to be a star, your mass has to be bigger than some minimum amount. If you just take a small ball of hydrogen, it won't be a star. If you get something big enough, you can have a star, and the limit is about 7% of the mass of the sun. Okay, if you take something which is 7% of the mass of the sun and above, it becomes a star. So what does it mean to be a star? It means that at the center of it, there are nuclear reactions. You burn hydrogen. You burn hydrogen. So you turn 4 hydrogen atoms. An hydrogen atom, basically the nucleus of an hydrogen atom is basically a proton. So you take 4 protons and you make helium out of them. Okay? Connecting it to the previous talk, helium is 2 protons and 2 neutrons, but we know that a proton and neutron can turn into each other. Okay, so this is what happens in stars. This is the same process that happens in hydrogen bombs, but in a more controlled way. And this is the thing that is producing the energy for the stars. So the star is cooling down from its envelope. Because it is hot, it emits radiation. And the energy that is lost from the envelope is being compensated by the nuclear energy that is being continuously created at the center. So this is why they live for so long. For example, our sun is going to live for 10 billion years. Okay? It's already passed about half of its life, and it has another half to go. If you take a mass which is smaller than 7% of the mass of the sun, you still get something that initially looks like a star, but the temperature at the center are not going to be high enough, and the densities are not going to be high enough to create nuclear reactions. And therefore, the thing is just going to cool down and die out as a brown dwarf. And that's not going to take too long. So if you have an object which is less than 7% of the mass of the sun, it initially looked like a star, but after a few million years, it cools down and you can't see it anymore. So these are called brown dwarfs. Planets are even smaller objects, but they're not only different because they are small, they're also different in their nature. They're made of something else. They're not usually made of just hydrogen and helium. Many of them are made out of other elements that we have in the universe, more rare, but still exist. Like if you look at our own planet, it's not mostly hydrogen and helium, as you know, right? We're standing on solid Earth. The center has lots of iron in it. It's a very different object than just hydrogen and helium. If you look at the planets in our solar system, there are 4 planets that are close to the sun. They have very little hydrogen and helium, almost nothing. If you look at the 2 giant planets, which are Jupiter and Saturn, they're mostly made out of hydrogen and helium, but we think they have a core, something in the center, which is more similar to our Earth. So they're also enriched in heavier elements than hydrogen and helium. So planets are not of cosmic composition. They have more heavier elements. They also orbit stars, so they're not independent objects. They always go around stars. People are talking sometimes about free-floating planets, which are in free space, not around the star, but we're not sure they exist. So the standard planets are always orbiting stars. So if I take an object that is not made mostly of hydrogen and helium, and I make it orbit around the star, would I always call it a planet? If it was the case, I could send a few astronauts to space, let them throw some stones into an orbit around the sun, and we have created new planets. So there was a decision not so long ago to keep the word planet only for major stuff, something big enough, something important. Planet is a big thing around the star. So there was a distinction between planets and dwarf planets. Planets have to be big enough so that their shape is controlled by the gravity, which is always going to make them what kind of shape? A sphere, yeah. The gravity will pull the object into a sphere, thank you, unless it is rotating rapidly, in which case it will be ellipsoid, like this one. Okay? So, these objects, as you see from the images, they satisfy these criteria. Their shape is dictated by the gravity. The Earth is mostly round, right? There are small corrections. There are the Himalayas there, and who knows what, some small dents in the sphere. But it's mostly a sphere. This is not enough. There was another requirement for an object to be called a planet, that its gravity is large enough to clear its orbit out of any other object. Okay? So if you look at the orbit, let's say, of the Earth around the Sun, there are no other objects with similar orbits. The next one is Mars. It's farther away, significantly isolated from the Earth. If you look at the asteroid belt, which is between Mars and Jupiter, there are many, many objects of different sizes, so we don't call them planets. Why? Because none of them has cleared all of the others from the surrounding. So the asteroids has many dwarf planets, but not planets. Okay, so we know what we're talking about. There are stars who have nuclear reactions in the center, planets, no nuclear action, not made of cosmic composition, but mostly of heavier materials, or at least some heavier materials. And the gravity is strong enough so they control their environments. If you remember, there used to be 9 planets in the solar system. Pluto used to be the 9th planet, but it failed to pass this definition that it has to clear its orbit, because Pluto is part of the collection of objects called the Kuiper belt, which by now we know has hundreds of thousands of objects. We have only measured maybe 1,000 of them, or slightly over 1,000, but we have some indication that there are many more smaller ones. And since Pluto didn't clear all the other ones, it means its mass is not big enough to be called a planet. So Pluto is now in this category, not in this one. So all the examples I gave you so far were from our own solar system. And for many, many years, up until something like 20 years ago, this was the only example that we knew of, the planets in our solar system. And there were questions like, is that the only planetary system? Our planetary system very rare. Is that 1 in every 10 stars, maybe 100 stars, 1,000 stars, 1 in a billion stars have planets around it? We didn't know. We only knew that our system, our solar system, have planets. And we believe that planets are the best places for life to evolve. It is definitely true for life in the form of you and me. We need a planet, right? We cannot live on a star, it's too hot. You can imagine maybe other forms of life could be in different environments. But life as we know it, they need a planet. So if we want to look for other places where life can exist, we need to know more about planets. We need to know where are the planets, are they abundant or not. So these are questions that people were asking for a long time. But in the past 20 years, there are amazing sets of observations which help us progress towards understanding these issues. And I'll try to talk a little bit about that. I understand that there was another talk by Tzvi Maze. Who attended that talk? Can you raise your hands high so I can see? Not too many. Professor Tzvi Maze gave both a talk and a discussion, I think. Okay, not too many. So I won't rush through any of this thing. I'll go more slowly. So the observations that are relevant for the subject are coming from 3 different directions, all helping us to understand planet and their formation. The first one, at least historically the first, that came first, is the observations of disks around young stars. So when a cloud of gas collapses under its own gravity to form a star, it has some angular momentum. The cloud may have some angular momentum, some rotation in it, and the rotation holds the collapse for a while, and some of the gas goes into a disk around the star. So as the star forms, as the star accretes from the gas that is collapsing onto it, a disk forms around it. And it is in that disk that we think the planets are forming. And this is probably why our planetary system is sort of planar. All of the orbits are more or less in the same plane. It's not that one orbit is like this and the other orbit is like that and the other orbit is, it's not random. They all seem to be more or less in one plane. So we think these all are a result of the original disk out of which the planets formed. So here are some images of these disks around other stars. So that was the first progress. We see that these disks are not rare. They exist around many other stars, and therefore planets maybe have the potential to form in them. Slightly later, there were discoveries of objects in the outer solar system. So at the outskirts of our solar system, beyond the orbit of Neptune, more or less where Pluto is, people discovered that Kuiper belt, that collection of objects. And we think that the Kuiper belt can provide to us a good laboratory for understanding planet formation. Because many of the processes that we think took place when planets were forming have their imprints on the Kuiper belt. So when we think, as I'll show you later, that when planets were forming there were many, many bodies of different sizes, all colliding to slowly create what we have today as the Earth. Okay? And we think that the objects we see in the Kuiper belt were on the process of making the same thing and didn't go into a completion. So we see many of them. So understanding all these objects and their orbits also gives us some understanding of planet formation. Maybe the most dramatic event is the discovery of actual planets around other stars. Today, we have indication for something like 2,000 planets, compared to 8 we had before. 2,000 planets around nearby stars. Okay? So, if before we had just one example, one star, our sun, with 8 planets around it, now we have thousands of stars with thousands of planets around them. Some only have one, or we know only of one planet orbiting them. Some we have full systems. Like this, this is a picture, it's not a real image. But there is a star with 6 planets orbiting it. So what I'll try to do in this 1 hour talk I have is to tell you a little bit about these discoveries. How do they do that? How do they find planets around other stars? And then, if I have time, I'll tell you what did it teach us about planet formation. How do we think it works? If you have any burning question in the middle, you want to clarify something, if you raise your hand, I'll take the question. Okay, so let's start with these disks. How do people find disks around young stars? And what did we learn from that? So here's a picture of what we think is happening. This is a cross-section. Okay, so if you look from above, you would see a star and the disk of gas orbiting it. Okay, so this is the star. This is the gas that surrounds it. And now I'm making a cross-section this way, and I'm showing the picture from there. This is this thing. So here's the star, and here's the disk. The disk doesn't get all the way to the star, but pretty close, and it's become puffier and puffier as we go further out. So how do we measure these disks? I showed you in the first image, maybe I'll go back to it, some images of actual disks. Here it is. Here's a disk. The star is right here in the middle. You can't see it because the disk is blocking it. Okay? So actually all the dark stuff in here, this is the disk that is blocking the star that is right here in the middle. And you can see only the top of the disk that scatters light towards you, from the star on the edge of the disk towards you. So these are disks that you can actually observe around young stars. But for most cases, you don't have these observations because the stars are too far and all this structure is too small. So even in the greatest telescopes we have, we cannot resolve these disks.
Okay.
Yes?
Is it a jet?
This is a jet, yeah. So as the stuff accretes, as the material accretes from the disk onto the star, some of it is ejected on jets perpendicular to the plane of the disk, both up and down. So what do we do instead if we can't really see it? We look on the spectrum of the star. So let's see. This is now intensity, how much energy you get, and this is the frequency of the light that you observe. Okay? So if you look in the visible light, which is around here, these are colors. So this will be purple, blue, green, and red. This will be the infrared, this will be the far infrared, and this will be radio frequencies. Okay? So what we think is happening is the following. The star is hot. It emits radiation mostly at high frequencies, at visible light, right, as we know from the sun. The sun emits its energy at, what is that, yellow, green, all the colors, right? So that's the sun, that's the star. But some of the light, because the disk is so close, is actually hitting the disk, warming up the disk, and the disk can't warm forever. What does it do? It re-emits that light. But since the disk is colder than the star, it doesn't get all the way to the temperature of the star. It re-emits that light at lower frequencies, at the infrared. Or even something in the radio, or some millimeter. So, this extra emission in the infrared is a signature of the existence of a disk close to the star. So if we see this infrared emission, which is above what we expect from the star, we know that there is a disk surrounding the star. So even though we haven't been able to resolve the disk from the star, we haven't seen it, we just look on the colors of the star and we see there is too much infrared there, we understand there is a disk. And this you can do for many stars, they don't have to be very nearby. And you can get some statistics. So what have we learned from that? A very important clue to planet formation. So on this axis is the fraction of stars that have disks. What does it mean they have disks? They show excess of infrared emission compared to what you expect from a star. And on this axis, you have the age of the star, which is estimated from some models. It's actually a difficult thing to do. So the age here is the log 10 of the age in years. So this is 10 million years, this is 1 million years, this is 100,000 years, and this is 100 million years. Okay? So what do we see here? You see sometimes the answer is 0. What does it mean? Stars whose age is 100 million years, they don't have infrared excess, meaning they don't have disks. But young stars whose age is less than 1 million years, 90% of them have disks around them. So these are good news in one way for planet formation, because it means that most stars had disks around them to begin with. There was a good chance for planet formation. It's bad news for planet formation because after 10 million years or 20 million years, there are no more disks. So planets, if they want to form, they have to do it fast. After 10 million years, there is no more disk. What happens to the disk is still a little bit unclear. Maybe it accretes into the star, maybe it evaporates when the star becomes too bright. But this way or the other, the disks disappear. And planets have to form fast, in less than 10 million years. Okay, let's go to the detection of extrasolar planets. Actually, the first detection of planet outside the solar system was done 20 years ago, exactly 20 years ago. But it was a strange system around the pulsar, and let me not talk about it. If you want to ask, you can ask later. The first method that was able to detect many planets around stars, and around stars which are normal stars like our sun, is radial velocity. And let me explain to you how it works. Here is a star. Here is a planet that orbits that star. So we used to think as the Earth is orbiting the sun, or Jupiter is orbiting the sun. What is actually happening, more accurately, is that they both orbit together the common center of mass. So if this is the sun, and this is Jupiter, it's not like this, it's a little bit like this. Okay? Now, why do we think that mostly the Jupiter is orbiting? Because Jupiter is much lighter, therefore its orbit is large, and the sun motion is tiny. What is the ratio of the sizes? Just inverse to the ratio of the masses. So if Jupiter is 1,000 times lighter than the sun, this is the case, Jupiter is 1,000 times lighter than the sun, then the orbit of Jupiter is 1,000 times bigger than the orbit of the sun. So you can neglect it if you want. The velocity of, do you know the velocity of planets around stars, like the velocity of the Earth around the sun? Who knows? What?
6 kilometers per second. So the velocity of the
Earth around the sun. 30 kilometers per second, pretty fast. Okay, we're right now moving around the sun 30 kilometers per second. Suppose I replace the Earth by Jupiter, where the mass is 1,000 times smaller than the sun. That means the sun is also moving. At what velocity? 1,000 times smaller. So instead of 30 kilometers per second, these are now 30 meters per second. 30 meters per second, what is that? About 100 kilometers per hour, like a car's speed on the highway. Okay? This is the velocity of the sun, because a planet like Jupiter is orbiting it. Okay? And it's measurable. You can now point your telescope to that star, and using the Doppler method, measure the velocity of the star. not of the planet. The planet is too dim, too difficult. But you can observe the star and very accurately measure its velocity. And what would you see? Suppose I am measuring the velocity from here, and the Doppler velocity method is such that it only enables me to measure the velocity in my direction. I cannot measure the velocity perpendicular to my direction, but only the velocity that is towards me. So if I'm standing, let's say, from here, now I see that the star is coming to me, going away, coming to me, and goes away. So I'll see a periodic change in the velocity of the star. I will understand from that that there is a planet orbiting that star. Okay? And okay, we'll go, maybe I should go now to the details of this method. So let's see an example. Here are actual measurements, one of the first systems, one of the first extrasolar planets that was discovered. So this is the velocity as a function of time, and we see that the velocity is changing. The star is coming towards me, going away from me, towards me, away from me. Okay? What can we learn from that? So we can measure this time from here to here. This is the time that it takes the star to complete one orbit. But that is identical to the time that it takes the planet to complete one orbit. They are doing the same motion. Just the star is a smaller motion, but with the same period. Okay, so I can know the orbit of the planet. I know Kepler's laws, which give me a relation between the distance of a planet from the star and its orbital period. As we know from our own solar system, planets which are far away take a long time to revolve around the star. Planets which are close in take a short time. What is that? For Mercury, it's 60-something days to go around the sun. For Neptune, it's more than 100 years. So there is a dependence on distance. So from the period, from how long it takes the star to complete an orbit like that, we can tell what is the distance of the planet from the star, without never seeing the planet. We just observe the star, we see that the star is coming towards us, then going back, coming again. From the period we can tell the distance. Okay, what is the amplitude of the motion telling us? So let's say, we already did that calculation. If it was Jupiter, we expect with velocity of 30 kilometers per second around the sun, like the Earth, then the sun would have a 30 meters per second velocity. Can you see what velocities they measured here? Much more. They measured 400 meters per second instead of, we estimated 30 meters per second. Why do you think that is? The planet is bigger, that's one reason, it's correct. This specific planet, I think, is 4 times the mass of Jupiter. Okay?
The planet is faster.
Yeah, and the planet itself is faster. Why is it faster? Because it's closer. Yeah. And how can we verify that? Because we can measure the time from here to here. And it turns out the period of this system is not 1 year, as we're used from the Earth. It's not 11 years, as we're used from Jupiter. It's 3 days. Okay, so what does it mean? It means that planet is sitting right next to the sun. This is a very hot planet. The temperature on this planet is above 1,000 degrees on its surface because it's so close to the sun. Okay, so this is a schematic picture of, no, this is a different system, of other system, but the planet is like here. It's very, very close to the sun. And this is compared to the planets in our own solar system. So this is the Earth orbit around the sun, but this planet is very, very close to the sun. So we discovered by this method of radial velocity lots of planets, hundreds of them, orbiting stars, but many of them have weird orbits. I already showed you one weird property, which is what? The very close separation between the planet and the star. But here I'll show you another one. Remember this picture of the velocity as a function of time? I'll show you another velocity as a function of time for another system. Look at this one. What do you think this is? So the velocity is going up, 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 and then very sharply goes down. And then again. The orbital period is now more normal. This is a 2 years, in case of 2 years. But why is this looking so strange?
The circular orbit.
Yeah, the orbit is not circular. The orbit is very eccentric. So this was a circular orbit, and this is a very eccentric orbit, a very elliptical orbit. So the planet is going around the star. It goes very slowly when it's far away from the star, and then very quickly passes on the near side to the sun and goes to the other side. So this is when it passes very close to the star. So we can learn something not only about the mass of the planet, the distance from the star, but also the shape of its orbit, and we've never seen this planet. We've just observed the star. In some cases, we measured maybe 5 planets around the same star, so we have actual planetary systems, and we have some estimates of the masses and distances of all these objects. This figure summarizes some of the things that we understood just from measuring these velocities of stars. This is an old figure, so it doesn't have all the information that we have today. We have many more x's in here that I can plot now. But each x here is a planet that we discovered around some star. This axis is the period that we see directly from the observations. So how long does it take the planet to go around the star? This period is measured in days. So this is 100 days, 200 days, 300 days, 365 days where the Earth is right here. This is 1,000 days, 10,000 days, 10 days, 3 days, which was the example I showed you before, is here. And the y-axis here is the eccentricity of the orbit. Do you know what eccentricity is? You have an elliptical orbit. It has a focus in here. This thing is called the semi-major axis. Or half of it is called the semi-major axis. This is called the major axis. And this thing so half of it would be A. And this is shorter than A because it's not a circle. And it's shorter by a factor of 1 minus E. So if E is close to 1, that means this is very, very short. If E is 0, it means it's a circle. So that's the eccentricity. It shows you how non-circular the orbit is. So for comparison, I also added in here the planets in our own solar system. So here's the Earth at 365 days, and with a very tiny eccentricity. So the Earth orbit around the Sun is slightly non-circular, but only in a tiny way, in a few percent. So Jupiter and Saturn, they're also on slightly non-circular orbits, farther away from the Sun. So we see here several things. One surprise I already told you, there are many objects on short orbital periods, very close to their stars. We did not expect that, even though they're as heavy as those planets. The other thing is that we see many planets on eccentric orbit, which we haven't expected either, because all we knew from our solar system are very circular orbits. So we don't know exactly what excites those eccentricities, what makes these orbits so crazily elongated. If I have time, I'll talk about it later. We do have some ideas why these objects, which are very close to the Sun, to their Sun, have circular orbits. Even if they had, in the past, elliptical orbits, their orbits would decay and become circular. And the way it works is the following. So if you put a planet next to the star, the planet is being pulled by the star. Okay. And that causes the planet to orbit around the star in a circle or an ellipse. But if you look in more detail inside the planet itself, the parts of the planet which are closer to the star are being pulled more strongly than on average. What does it make? It makes a bulge on the planet that points towards the star, because this is pulled more strongly. If you look on the opposite side, away from the star, the particles there are being pulled towards the star less than average. So instead of moving with the planet, they are a little bit lagging behind, and it causes a bulge to the other side. Is that phenomena familiar to everybody? These are the tides that we have on the ocean in Earth from the moon. Okay. So what if that planet that goes around the star has an eccentric orbit? What happens to the amount of the tides that make the planetary shape, instead of spherical, elongated? How much elongated does it become when it's close to the star, and how much elongated when it's farther away from the star? So it turns out when the planet is close to the star, these differences are more significant, and the planet is very elongated. When it's far from the star, then the center and the edges are slightly different, but compared to the huge distances that we have, it's less significant. So as the planets orbit around the star, the planet's shape is changing as a function of time. So when it's close to the star here, it's like that, and when it's far away from the star, it's more spherical. So the planet is doing this. And there is some dissipation associated with that motion. And that dissipation, as time evolves, causes the orbit to become circular. So this can be calculated, and this is this upper limit showing by this line. Anything that is above this line should have decayed to small eccentricities. Far away from the sun, that doesn't happen, so if you had an eccentric orbit, you can keep it. We don't know why you have that eccentric orbit, but if you had it, it can stay. Here, if you had an eccentric orbit, it must have decayed by tides. All that phenomena is, as we said, similar to what the Earth and the Moon are doing. So if you want, with some exaggeration, oops, where did that go? The Earth is being elongated by the Moon. See, it's not really a sphere, it's elongated with the long axis pointing towards the Moon. Mostly on the ocean, but even the solid Earth is doing that to some extent. And actually, these tides between the Earth and the Moon, they cause the orbit of the Moon to evolve. We believe that the Moon was once very close to the Earth. It was orbiting around the Earth in less than 6 hours. And because of these tides and complicated things with this tide, not so complicated actually, the Moon has evolved to where it is, and it's going to continue to evolve. And the month, which is the time that it takes the Moon to go around the Earth, is getting longer and longer every minute. Okay. Let me go to the second way that planets were detected, which now become the major way in which planets are detected, which are transits. Okay? These are planets which pass in front of the star for a given observer. So let's say this guy over here is our observer, and he's looking at my head, which is the star. And if the planet is orbiting the star just this way, it will pass between the star and the observer. If the planet was orbiting the star this way, it never passes between the star and any of you as observers. If it's this way, then only those observers can see it. And the way that this transit can be seen is that it blocks a tiny bit of the light of the star. Okay? If you want to remember some numbers here, the size of Jupiter is about 10 times smaller in radius. The radius of Jupiter is 10 times smaller than that of the Sun. It has about the same density as the Sun. So you remember we said that the mass ratio is 1,000, and the radius ratio is 10. 10 cubed is 1,000, it all works out. Okay, and the Earth is 10 times smaller than Jupiter. So 100 times smaller than the Sun in radius. Okay? What does it mean? When a planet like Jupiter is crossing in front of a far star, it blocks what percentage of the light?
Very small.
Exactly how much if it's 10 times smaller than the Sun in radius? 100. So 1% of the light of the star is going to be missing. So here are a few guys that went with a telescope and looked for that effect. They measured the intensity of the star as a function of time, and here they saw a dip, and then it came back. And then they saw that this dip is periodic. It comes again every 3 days. So every 3 days that planet is going in front of the star, blocking 1% of its light, going again, and then 1% again. This is the same star viewed from the Hubble Space Telescope, where the atmosphere doesn't blur your image and doesn't make all the noisy stuff. And therefore you can see a very nice thing. You can see this dip and rise. And what did you calculate? 1%? Is that what's observed in here? Slightly more. 1.5%. What does it mean? It's larger than Jupiter. This is not Jupiter, this is a larger object in radius. How can we know the mass of this object? We can go to the other method, the radial velocity. We measure the velocity of the star, we see how the planet is shaking it, and we know. So when we combine these two things, we know the density of the planet, because we measure from this method the size, from the other method the mass, we combine, we get the density. This is the launch of a space telescope called Kepler, which was launched 3 years ago. And it basically observes something like 100,000 stars, 150,000 stars in a given piece of the sky all the time. And what does it wait for? Just for them to blip a little bit, and then come back to their normal intensity. And if you see that periodically, you know there is a planet going around that star. These are some results of Kepler published not so long ago. So 150,000 stars, they found 2,300 and something of these stars were having this phenomena that the light goes down for a little while and then come back. So these are probably planets. You can't be absolutely sure because there are other ways to do these dips. But these are most probably planets. From the period of this thing, you know the distance. And therefore, if you know the distance, you know the temperature on these objects. And 46 of them have the right temperature. Right temperature for what? For life. This is what we all want at the end. So right temperature means here between 0 and 100 Celsius. Why? This is what they decided to call it interesting. 0 to 100. Several hundreds of them are systems, which means you see at least 2 planets orbiting the same star. So what we learn from that is planetary systems are not rare. They are abundant, they are all over the place. Okay? More than 10%, probably more than 20% of stars have planets around them. Okay? There are many billions of stars in our galaxy, and if just 10% of them have planets, it means there are many billions of planets in our galaxy. So now it's your turn to estimate what is the probability that there is life in the galaxy other than here. We don't know exactly what it needs, but if there are 10 billion chances, seems probable. Let me skip this. Maybe I'll say it just in one word. I told you we can calculate the density, and some of these densities of these stars are lower than we expected. They seem to be puffed up compared to what our theories would predict. So we have to understand something about the interior structure of planets, or maybe something about how they cool. The dip won't be 1%, even if the other star is not luminous at all. Okay? But there are other effects that can confuse you. For example, you have this star and another comparable size star, so it makes a dip of 50%. Okay, so I can rule this out easily. But behind it, completely unrelated, there is another star, which is 100 times brighter. All of a sudden, that 50% out of that becomes 1%, and you think it's a planet. So there are all these confusions, and they have method to see from the spectrum of the transit sometimes, from the shape of it, from many indications, that it's probably one system or the other. Okay, sometimes they can't tell, and this is why they call these candidates. Because these effects, like you mentioned, could be. You can ask statistically what is the probability of that, and they conclude that probably 90% of these are planets. But maybe 10% could be things of the sort you're saying. There's another fascinating method. Unfortunately, so far didn't work so well to detect planets. It only worked on a handful or a few dozens of systems. And this is microlensing. So let me skip that so I can get to some other stuff. Remember, there's a way with gravity, that gravity deflects light of objects, and you can see the gravity of the planet on some background stuff. I already mentioned this part, that we're looking for planets which are the right distance from the star so that the temperature will be right. Now, the distance cannot be, it's not an absolute number because it depends on the star that we're talking about. If it's a bright star, you want to be far away. If it's a dim star, you want to be close by. So there is a band here. This is distance, and this is the mass of the parent star. So if the star is small, you want to be close. If it's big, you want to be far. And some of the planets that they have detected do have the right temperature, so we think. So they can at least potentially host life. Here's just a word of caution that we know that in the most extreme environment we have on Earth, there is still life. Even in this boiling water, I think this is from Yosemite, all these colors here are bacteria that are growing in this boiling water. So it means even when the temperature is 100 degrees, you can still have life. So I'm not sure that 0 to 100 is absolutely necessary criterion, but it definitely helps for life in the form that we're used to. Okay, in the few minutes that I've left, let me say a few things about what do we think are the processes that are happening to these planets, how they evolve. So as I told you, we discovered those planets which are much closer to the star than what we were used to. How did that happen? We have theories of planet formation that I'll mention in a few seconds. And they all suggest that planets form far from the star. Close to the star, it's too hot. Especially planets that are made out of hydrogen and helium. The hydrogen will just evaporate. If it's so close to the star, it will never accrete to a planet. But even objects which are like the Earth probably can't form too close to the sun. So what we think is happening is the following. You form the planets where you think you can form them, far away from the star. But you remember, they form in this disk of gas that is surrounding the young star for 10 million years or so. We measured that. Then there is friction between the planet and the disk, and we think that that friction caused the planet to migrate. Calculations show that this migration is mostly inward, so it causes the planet to move towards the sun. I believe that many of the planets that formed this way may have destroyed themselves by this friction and fell all the way to the star. And what we see are the last survivors of this process. So this is an image of a numerical simulation that has a star in the middle and a disk of gas around it, and here there is a planet, and that planet makes perturbation on that disk. Those perturbations, in some way, which I'll explain soon, cause some friction and cause that planet to migrate towards the star. There is a chance that this interaction between the planet and the disk also causes the high eccentricity that we see. This is under debate. Some people's theoretical calculations say that the planet-disk interaction caused the eccentricity to vanish. So even if you put something on eccentric, it becomes more and more circular. Some people say that it actually, in certain circumstances, can cause the eccentricity to increase. So it is still under debate. Let me keep that for one more second. Let me show just one movie, and then I'll finish. So here's a movie that summarizes many of the processes that we think takes form in the formation of the cores of planets. So you remember, there are several kinds of planets. Some are made mostly of hydrogen and helium, these gas giants that we have in our solar system, and also around other stars. And some more like the Earth, which are mostly solid. Even the gas giants, we think they have a solid core in the middle. So this cartoon explains how these cores form, or as how the Earth forms. So we think there are planetesimals, building blocks of these planets. We're not sure what their initial size is. For this reason or another, we believe 1 kilometer. Okay, so each of these dots is a sphere of 1 kilometer in size orbiting the sun. There are gazillions of them orbiting the sun, and they can collide with each other or with a larger object and accrete on it. And that larger object can become larger and larger and larger. If that was the whole story, they just randomly collide, it turns out it will take 100 million years to form the Earth, and maybe 10 to the 12th years to form Neptune. 20 to the 12th is good or bad? It's bad, because the universe does not exist for 10 to the 12th years. So we need something else to help out. And it turns out the thing that helps out is what we call gravitational focusing, which is shown in here with this white line, white circle. So you see, if this is the planet that is about to form, and it tries to collect objects that are coming and collide on it, it has a small cross-section. This is why this process is relatively slow. But it has gravity, and gravity can deflect the orbits of faraway objects and cause them to collide with the growing planet, therefore increasing its effective cross-section, and the rate becomes faster. So this circle marks the size of the effective cross-section of the planet due to the aid of its gravity. For this to be effective, you need all the velocities in the system to be small. Why is that? Suppose that one of these planetesimals was very fast, then it wouldn't notice the gravity of this object. It would pass too fast, and the gravity would be too weak to bend its orbit and to accrete it. So this accretion process is enhanced only if this object is big, that has a lot of gravity, and all these planetesimals are moving relatively slowly. So all this has to be understood and taken into account when you want to understand how planets form. Maybe I'll leave that to the discussion in the next talk. Let me summarize here. So we're looking for new worlds. There are disks around most young stars, 90% of them. There are thousands of planets that have already been detected, and from that you can estimate what's the frequency of planets, and it's about probably more than 20% of stars have planets around them, so they're common. These planets have unexpected orbits, very close to the stars, very elliptical. Missions like Kepler, flying out now or in space, can find Earth-like planets because they can see small dips in the light. We didn't calculate how much it is. We said that the Earth is 100 times smaller in radius than the Sun. So how much light is missing when the Earth is passing in front of the Sun? 10 to the minus 4, yes, out of the light. So you need something very, very sensitive. And Kepler was designed just so that it can do that. Okay, so you can see planets like the Earth passing in front of the Sun. Unfortunately, the distance for most of these stars, even the nearby stars, is not so tiny. The nearby stars are a few light years away from us, and most of the stars for which we detected planets are 100 light years away. And if you take the stars that Kepler discovered, there are thousands of light years away. So suppose in a few years or a few decades, we do discover some evidence that there is life. Can we really do something with it? It's not so clear. So it will take 100 years to send any message, another 100 years for them to reply to us. Communication could be problematic. Also, you can ask, can I transfer any meaningful amount of information? If they have a receiver, let's say with the same technology that we have. This is the biggest radio telescope we have on Earth, a receiver. 300 meters in diameter, huge. So the bigger the dish, the more powerful signals you can send. And if they have a similar thing on their planets, several hundred light years away, it turns out they can still sense the signals we can send, and we can still send on a reasonable bandwidth some meaningful information. For example, if you want, we can probably send the information about our DNA, maybe the cat's DNA, within a year, given the current technology, if they have the same thing. So we can communicate meaningful information, but it takes a bit too long. Is that useful or not? You decide yourself. Thank you.
Okay, we have time to take a few questions, so please raise your hands. Yeah.
So while observing the intensity of some star, if the transparency of our sky changes in clouding, then how can we use that effect?
Or if we have clouds on our planet, how can I see these dips?
No. If there is change in transparency of the sky while observing the intensity, initially there was clear sky, but in the middle, the clouding, due to clouding, the transparency changed, and of course that would affect the intensity of the star. Then how can we use this effect?
Okay, so we're mostly trying to do observations of stars when there are no clouds. If there is a cloud, we just forget about it. Okay? Even in clear sky, completely clear sky, you know, telescopes on the Earth are chosen. Okay, if you didn't hear the question was about the effect of clouds. When you observe stars, clouds can come and change the transparency and therefore affect the intensity of the stars that we measure, and we may think it's a planet around the other star, but it's actually a cloud in our atmosphere, which is not what we're interested in. So it turns out that the big problem is not what you're saying, some similar effect which is called scintillation. But clouds, when there are clouds, you just don't observe. Okay? When there are no clouds, if you go to a high mountain, hopefully above most of the clouds, and or in a good desert where it's dry enough and there are mostly clear days, there is still always perturbation from the Earth's atmosphere because the density of the Earth's atmosphere is not uniform. Because there are hot cells and cold cells, so when light from a star comes in, it gets distorted. And that causes these fluctuations that I actually showed you here. Where was that? Here. You see in this figure, all this is caused by scintillation in the Earth's atmosphere. So all these fluctuations are due to the Earth's atmosphere. And there's a problem, we cannot get rid of that. Not easily. Okay? So the way to go from here to here, which is much less noisier, is to go to space.
By taking a reference star and by calculating the relative change in intensity, I think we can change this.
No, because this scintillation is very local. So there could be patches of size of 10 centimeters high in the atmosphere that do this. So if you look at this star and the other star, it's already different. So it's not a coherent effect over the whole sky. If it was the cloud thing you were mentioning, yeah, you can do something like this, and people do those kinds of corrections. Yes?
Why doesn't our solar system have hot Jupiter?
Good question. So we said, we think, okay, the question was, why does our solar system doesn't have a hot Jupiter? Why don't we have a planet the size of Jupiter or any other size orbiting the star with a 3-day orbital period? So, as I said, we think most of the planets form far away from the star, and some of them migrated. Now, the first systems that we discovered, they all had planets which were close to the stars. This is a selection effect, because those are the stars which are easier to detect. They have short orbital periods, they have strong gravity on the star, so the star is shaking fast. So first we only detected those. As time progresses, we detect more and more systems with regular Jupiters, not hot Jupiters. Still the question is why some systems have hot Jupiters and some systems don't. We don't know. We think that migration, which is this friction between the planet and the disk, caused the planet to migrate. But the time scale for migration is not so short. It's actually long, maybe 1 million years. Okay? What does it mean? And you remember that the disk is there for a comparable time, maybe a few million years also. So since those times are comparable, it may be that some systems had time to migrate, And in some systems, the gas disappeared shortly after the planets formed, and they're there. So we don't know, but because these two timescales are similar, we think it could be this way or the other way. So in our solar systems, it seems to be that no major migration happened. The planets are more or less, we think, in the place close to where they formed. Yes?
Do the formation of the moons as they which orbit around the planet as the same as the formation of the planets around the stars?
Say that again, formation of the moon
Yeah.
has the same what?
Same which the formation of the planet.
Same what?
Same what?
Same time scale, same...
Same formation, same ways of formation.
Oh, okay, same way, okay. Good. So how do moons around planets form? That is the question, basically, if they form in the same way. So some yes, some don't. There are different kinds of moons. We think some moons were actually captured into orbits around their planets. We think our moon formed in a giant collision between maybe a Mars-sized object and the Earth, and that giant impact created debris around the Earth and formed those debris in actually a similar way to that movie I showed. These debris agglomerated to form the moon. So in that sense, it's similar. The moon is now migrating outward. There's no disk, but because of the tides on the Earth, it's migrating outward. But in a way, there are some similarities. We think the moons around Jupiter formed even more, their formation is even closer in mechanism to the way stars, planets formed around stars. So I would say, if you want one word answer, yes. Yes?
Yeah. In binary star system, an star and a black hole orbit each other out.
I only heard part of it. In binary stellar systems?
Yeah, an star and a black hole orbit each other out.
How do binary systems orbit each other?
Yeah.
Okay. So it doesn't matter if there's two stars or a star and a black hole, it's the same thing. So you have gravity, and if you have some initial velocity which is not towards each other, you'll get an orbit. I'm not sure at what level you're asking, but if you're asking, say, okay, it's the same way the Earth orbits around the Sun. How is the Earth orbits around the Sun? Just the same way. So you have the Sun, and the Earth here has some velocity in this direction. If there was no gravity from the Sun, the Earth would just continue all the way straight. But the Sun is pulling the Earth, so it adds velocity in this direction. Now it's moving this way, and the Sun is pulling it again. And that causes an orbit. Same thing for binary star, same thing for black hole and a star, same thing for binary black holes. Is that the question you were asking?
Yeah, it's a question raised. The question is the black hole itself can be seen, but the X-ray from its acceleration rates can be detected. How? It is one question.
Say that again. If what?
Starting a binary star system in which an ordinary star and black hole orbit each other.
Yes.
The black hole itself can be seen, but the X-ray from its acceleration disk can be detected. How?
Accretion disk. Yes. The accretion disk just emits X-ray, and you can directly observe them. The accretion disk, when it accretes into the black hole, is so hot that the temperature, instead of emitting optical light, they are such that they emit most of the energy in X-ray. And those X-ray you can see with an appropriate telescope. Okay, so you can see the emission from the X-ray, and understanding the spectrum of that X-rays tells you something about where that disk is compared to the black hole, and maybe something about the mass of the black hole. Does that answer? If you want the mass of the black hole, the easiest is probably to get it from the orbital period of the binary. If you have enough information about that, you can get the mass of the black hole. Yes?
If I have an initial cloud of gas and dust, because the those cells are disk, why should it form a disk? Why can't it form any other shape and continue conserving its angular momentum? Why should it flatten into a disk?
Okay. So if you just think of conservation of angular momentum, there are gazillions of shapes it can form, right? You give me the shape, and then I'll tell you how quickly to rotate it to conserve angular momentum. That will be the end of it. But it turns out that there are always mechanisms that dissipate energy in that object. Okay? So let's say collisions between dust particles take some kinetic energy into thermal energy, which is then radiated away by photons. So energy is being lost from the system. So now, the story is that energy is being lost from the system much more quickly than angular momentum is. So let's say you take conservation of angular momentum, and you force me to reduce the energy of the system. This will cause a flattened disk. So, suppose you have a thick disk, just to make it simple, we're already going towards the end. A thick disk and a star in the middle. And you have dissipation in the disk. Dissipation can, without losing angular momentum, only flatten the disk. So if you sprinkle some random stuff around the star, you come back after an appropriate time, after a few collisions between the particles, they will all lie in a disk around that star. The disk will be very thin. And a good example to understand these kind of phenomena, I won't show you but these are the rings of Saturn. Okay, the rings of Saturn are just what you were saying. They always collide with each other, so they dissipate energy, but they have nowhere to release the angular momentum. So the lowest energy state with a given angular momentum is that of a disk. Yes?
We have time for another 2 questions.
Okay.
You said the Earth and the Moon slowly separate from each other because of the tides of the Earth.
Yes.
Shouldn't the gravitational pull of the Earth between the Earth and the Moon somehow negate that effect?
No. So, if there were no tides, then just the gravity between the Earth and the Moon will cause the Moon to orbit the Earth. Just as the 2 black holes orbit, or just as the Earth orbit the Sun. Okay? So just 2 objects, only under the gravity with no tides, will just cause them to orbit. So let me tell you how the Earth-Moon system evolves. It's actually a fascinating story. So here's the Earth, here's the Moon. Let's say that the Moon is orbiting this way around the Earth, okay? But we said there are tides on the Earth. How do the tides look? They are high in here, and high in here, low here, and low here. The tides make the Earth look like this. Right, I mentioned it. I'll explain that again. Here, the particles here are being pulled toward the Moon stronger than average. Average would be here. So they go more towards the Moon. Particles in here are being pulled towards the Moon less than average. So they lag behind. So there's also a bulge in here. So this is the way the Earth looks. And the way I told it, you would think that points exactly towards the Moon. But the Earth is spinning faster than the Moon is orbiting the Earth, right? So we can think of the Moon as staying in its place, and the Earth is spinning. The tides are always pointing more or less towards the Moon, and the actual features on the Earth, where the Himalayas are, where the Atlantic Ocean is, spins under this configuration. So let's say if this is the Atlantic Ocean, at one time there is a high tide in here, and then when the Earth spins this way, now there is a low tide in the Atlantic Ocean. Okay, so because of the spin of the Earth, and because of some friction between the ocean and the solid Earth, the tides are being carried by the spin of the Earth. So they're not pointing directly towards the Moon, they're slightly ahead. So instead of this, they're like that. So this would be Earth with no tides. This is Earth with tides, but no dissipation, no friction. And this is Earth with tides and with some friction. So now this is the shape of the Earth. And now you can think of the gravity of the Earth as having 2 components. One from the Earth, which is more or less spherical, and the next one from this bulge in here, which tends to pull the Moon forward. That means it gives energy and angular momentum to the Moon, and this is why the orbit of the Moon changes in time. what is the reaction of that process on the Earth? So think of the moon as pulling this bulge backwards. So what does it do to the Earth? Slows the spin of the Earth down. So the energy into the orbit of the moon is coming actually from the spin of the Earth. And you remember I told you that the moon started with an orbital period of 5 hours. No, this was not true. The Earth was spinning. I said it wrong. The Earth was spinning with a spin of 5 hours, 5.7 hours. How do we know that? How do we calculate that? We simply take all the angular momentum of the moon and we put it in the Earth. And then you will get an object that is spinning at 5.7 hours. And that process just pushed the moon out. And now most of the angular momentum of the Earth-Moon system is actually in the moon, no longer in the Earth. And in a few more GB years, it will be even more so, and the Earth will slow down. Until when? Until the spin of the Earth equals the orbital period of the moon. And then the bulge will always point towards the moon, and there will be no exchange of angular momentum anymore. And this will happen when the orbit of the moon will be somewhere here, where its period will be 50 days instead of 20-something days that it's now, almost 30 days. And the day, the spin period of the Earth will also be 50-something days. Okay? So we're evolving towards very long days and slightly longer months.
Okay, and sorry, I've been told that this was the last question already, so we're out of time.
So next session is at 2, you can ask the question then.
So thanks again.